These are the video notes for Objective 1A, function notation. So in these notes, we are going to be covering function notation through three types of problems. The first type of problem is evaluating a function. The second type is combining functions. And the third type is composition of functions. This video will cover the first two operations with functions, evaluation and combining, and will correspond to chapter 1.1 in your textbook. The second video, or part 2 of this objective, will cover composition and will correspond with section 4.1 in your textbook. So let's begin the notes with what a function is and what function notation is. A function is a relation that associates each element in the domain with exactly one element in the range. When we write a function, we use any letter of the alphabet, parenthesis, any letter of the alphabet for the input, and this notation is read aloud as f of x. Or better yet, if you start saying the value of f at x, because this expression right here represents the output of the function, whereas the x represents the input. So when you see f of x, remind yourself that this is the value of the function at whatever input you see in the parentheses. So let's look at our first example in our notes, and let's take a basic function equation. Functions come in many forms, and we'll see quite a few forms during these notes. The question is, what is f of 2? Well, if we're using the same wording, we're saying, what is the value of f when x is 2? Or what's this equation when x is 2? So we plug in 2, and we find that f of 2, or the value at 2, is 9. Example 2, we're going to take a more complicated equation, and we're going to find a lot more expressions evaluated there. So let's erase. For our next equation, we're going to do f of x equals 2x squared minus 3x. This function has two input values. Both inputs will need to be replaced anytime we attempt to evaluate. So a, f of 3 equals 2, 3 squared plus 3, 3. Feel free to use your calculator to evaluate any order of operations expressions. In this example, we have a result of 27. The next one, f of x plus f of 3, is requiring a little bit more finesse. So when we write this one down, we are going to copy the entire f of x function, and then at the end, we're going to add our expression for f of 3. Try each of these evaluations before I get to the solution. That way, you get an idea if you're able to do these types of problems independently, or if this is a type of skill that you're going to need to practice more. The next one in the notes is 3 f of x, which means take the value of f at x and multiply it by 3. Or in this example, multiply both terms of the expression by 3. The next one is f of negative x. For this expression, we're going to be inputting a negative in for the input. So, and we'll compare it to negative f of x, which is different. F of negative x, if you know the difference between odd and even functions, this is even because the exponent is 2. This is odd because the exponent is 1. You know that negatives turn to positives in an even function, and that negatives stay negative in an odd function. So you might know to switch the sign and keep the sign. But if you don't, we can just input negative x squared and simplify the expression from there. A negative squared is a positive, and a negative times a negative is a positive. Because one term stayed the same and one term changed signs, we know that this function is neither odd nor even. It's actually a combination of both, which is why it doesn't behave like odd and even functions might. Let's compare that to putting a negative on the output instead of on the input. If we take a negative to the entire function, we're going to have to change both signs on both terms of the expression. And we get a different output than when the negative was on x. You can't see it. All right, let's try the next example in the notes. So for the next example, we're using the same equation. I don't know why I erased it. But this time we're going to evaluate f of 3x, and we're going to compare that to f of x plus 3. So we need to replace every input variable with a 3x instead of an x. Now notice the 3 is included in the parentheses for being squared. That's an important step when inputting an expression into a function. Here, we don't want to do 2 times 3. We want to follow our order of operations, which say to do the exponent first. And so because our calculators don't do expressions with x's, this is an order of operations questions we need to do by hand. 3x squared is 9x squared. 3 times 3x is 9x, keep it negative. And then we need to multiply the 9x squared by 2, and we get 18x squared minus 9x. Let's compare this input of 3x with an input of x plus 3. Inputting x plus 3 for each of the x's in the expression looks like this. And again, because we're talking about expressions with x, we can't just type this into our calculator and simplify. We're going to need to complete these operations by hand. Do not, under any circumstances, distribute the squared. A quantity squared is that quantity multiplied to itself. In this case, we're doing a binomial times a binomial. So that's going to require full distribution. X times x is x squared. X times 3. 3 times x, and 3 times 3. Now you may have noticed I distributed the negative 3 out to the x plus 3. This is a separate operation, and because it's from a separate term, it can be evaluated while doing another step. Just make sure that you bring it down each time until it's time to combine it. We're now going to distribute the 2, but at the same time, I'm going to combine these. So 3x plus 3x is 6x. And 6x times 2 is 12x. At this point, we need to combine like terms. 2x squared, 12x minus 3x is 9x, and 18 minus 9 is 9. So f of x plus 3 equals this expression here. The last example in function notation or evaluating function notation is actually a pre-calculus. This is called the difference quotient, and it's one of the ways that we find the derivative of a function. So let's complete the entire difference quotient and just make sure that we leave ourselves enough space because there's quite a bit of scratch work that goes along with this example. We're going to do f of x plus h minus f of x all over h. Let's start with the first expression, which is f of x plus h. So we're going to take our equation and input x plus h. Now, in this space right here, I would need to subtract f of x, and I'm not quite ready to do that step, so I'm going to leave this here and come back later. So first, I need to distribute x plus h to itself, but I can go ahead and distribute my minus 3x minus 3h. Similar operation that we did last time. Add these two together before multiplying by 2. And then we're now ready to subtract f of x. So what I'm going to do is I'm going to take this expression and write it farther to the left. 2x squared plus 4xh. And then I have to be careful because I want to subtract the original function. So I'm going to subtract 2x squared, and I'm going to subtract a negative 3x, which actually means I'm adding it. You can see that the 2x squareds will now cancel. The 3x's will now cancel. And we don't want to forget that the entire expression is over h. So this h in the denominator will divide out any h in the numerator as long as we pull it out of every single term. So if we pull an h out of every term, we're left with 4x plus 2h minus 3. And that is the derivative. A graph can be a function just like an equation and can be evaluated, but we need different techniques when evaluating a graph instead of an equation. Remember that a function is the value of f at a given x. So if we name this graph f, and we see the first question in the notes as f of 0, we're being asked what is the value of this graph at x equals 0. And so with graphs, we organize our input-output as ordered pairs. What we're really looking for is the ordered pair when x equals 0. So let's look at our graph. X equals 0 is here at the origin, and the output when x is 0 is 4. So we can write that f of 0 is equal to 4. And then we just need to repeat that process to make sure that we understand the input-output process. F of 4 means to find the output when input is 4. So if we're thinking about our ordered pair, the ordered pair is 4, 0. And the last question in the notes, f of 2, is what our ordered pair is when we have 2, and it looks like 5. This is how you evaluate function inputs given a graph. We're going to do something similar in the next example with function tables. Function tables behave similarly to function graphs. So when you're evaluating a function table, you're looking to complete that ordered pair. For this example in the notes, we have 3 questions: f of 0, f of 3, and f of 5. Now there's not a lot of options with these ones, but we want to remember that inputs are always found in the left column and outputs are always found in the right column. So if these expressions weren't found in the left column, we would say does not exist. In this case, all 3 are here, so f of 0 equals 0, or the distance driven after 0 time is 0. F of 3 equals 40. The distance driven, I'm just assuming a context here, the distance is 40 after 3 units of time. And then at 5, we see that the distance is 0 after 5 units of time, which indicates that the story has returned to the starting position. This is the end of what you need to know to evaluate a function. Be sure you can evaluate a function even presented in different forms, not just functions presented as equations. For the last part of this video, we're going to go ahead and combine functions using our standard operations of addition, subtraction, multiplication, and division. For the next section of our notes, we're looking at f of x equals 2x plus 1 and g of x equals 3x minus 2. Our first question is to find f plus g of x, which is asking us to add the 2 functions together. So we'll write f plus g, and then we do not write another x. This x is just to indicate that the input variables should be indicated by the variable x. So the fact that we have x's in the problem is why this says x. When you're doing this, you want to simplify the function as completely as possible within your knowledge. So 2x plus 3x is 5x, positive 1 with negative 2 is negative 1. And my answer to part A is 5x minus 1. B is the same or similar concept, except it's subtraction, which means we need to pay attention to our positives and negatives. In this case, we're going to put g first. And then because we're subtracting an entire expression, we want to use parentheses to group the 2x plus 1 together. This also gives us a reminder that we're subtracting 2x and we're subtracting 1, or that the negative needs to be distributed, which is saying the same thing. 3x minus 2 minus 2x minus 1, fully simplified, becomes 1x, or just x, minus 3. The next two operations are addition and quotient. So addition, multiplication and quotient. So let's multiply these two expressions together, which is another good practice of multiplying binomials. For f times g of x, we want to take 2x plus 1 times 3x minus 2. Our result is 6x squared minus 4x plus 3x minus 2. Or final answer, 6x squared minus x minus 2 when fully simplified. The amount of simplification expected for you on quotients is not as intense as the amount of simplification expected for addition, subtraction, and multiplication. So let's take a quotient where g is in the numerator and f is in the denominator. G is 3x minus 2, f is 2x plus 1. Since neither of these expressions have any factors in common, you would not be expected to simplify this particular expression any further. But you do want to indicate that you understand the restricted domain when looking at a quotient. Denominators can't equal 0. So if 2x plus 1 cannot be 0, that tells me that x cannot be negative 1/2. To reach this solution, you simply solve the equation, minus 1, and divide by 2. Anytime you're creating a quotient or combining functions in a quotient, you want to check your denominator and identify the restricted values. The last question in this section of the notes is, what are two different ways you could evaluate f times g of negative 2? And it's a really good question, so I'm going to leave my answer for f times g visible and just erase my quotient. So the first way that you can find f times g of x, especially if you've already found f times g of x as an expression, is to just plug in negative 2 to your product. That's just to say negative 2. So one option is to first find f times g and then plug in negative 2. Go ahead and use your calculator to evaluate this expression. I am getting 24. Well, if this way works, why is there another way to evaluate f times g of negative 2? Imagine you hadn't already found f times g in a previous question. One way to evaluate f times g of negative 2 is to find f of negative 2 times g of negative 2, which is actually how we define the product of two functions. We just think of it as this function times that function. So let's evaluate f of negative 2. 2 times negative 2 is negative 4, plus 1 is negative 3. Now let's evaluate g of negative 2. 3 times negative 2 is negative 6, minus 2 is negative 8. Well, what's negative 3 times negative 8? And we get the same solution either by first finding the product and then inputting negative 2, or by finding negative 2 for each function and then finding the product. So this concludes the video notes for part 1 of Objective 1A, function notation.